Hello everyone, and welcome to the final video for Unit 3, Angular Motion. In this video we will be exploring the two components of angular acceleration. They include normal and tangential acceleration. Tangential acceleration is due to the wheel's speed changing. That means the magnitude of v and omega values. Now when I say wheel, it could also be an arc. So if you had an arm that's rotating, then it's the arc about which this arm is rotating. Tangential acceleration occurs tangent to the arc of travel, perpendicular to the radius. So this is very similar to the tangential velocity. Whereas normal acceleration is due to the change in direction of velocity, and it occurs along the radius arm. I'm going to draw some figures here to help explain the two components of acceleration. So we are going to start with an object here, and it has a radius arm about which this disc or this wheel or gear, however you want to look at it, about which it rotates. So here's the radius arm out to the edge, and call that R. As I said, it is rotating, and it's rotating with a certain acceleration, angular acceleration alpha, and angular velocity omega. So we can pick any point along anywhere on this wheel. I'm just going to go ahead and pick a point straight out along the horizontal line here to the extremity of this wheel. And we're going to call this point 1. Since the wheel is rotating clockwise, we see that's based on the direction of the velocity, and it's also accelerating in this direction. First thing that we can say is that we do have a velocity, a linear velocity, and that velocity is tangent to the wheel. So in other words, it would be located like this. So this would be v1, and it is 90 degrees to that radius arm. Similarly, our acceleration is located here as well. So our acceleration, but this is tangential acceleration. Again, that is due to the fact that we have a linear velocity that is increasing at this point. So that magnitude is changing. So we have a tangential acceleration. That point, as it rotates about the center, is changing direction, constantly changing direction. We said before that there is an acceleration if we have a change in magnitude of velocity or if we have a change in direction, and that's what we have here. And as a result, we will get a normal acceleration, and that acceleration occurs along the radius arm, as we see here, going back towards the center. Here is our normal acceleration. We can repeat this process at any other points on this wheel. For example, I could pick a second point up here, and we can draw in our tangent accelerations and velocities. So they would occur tangent or 90 degrees to that radius arm. This is always the case. So again, our velocity at point 2 is also our tangential acceleration, and again we would have a normal acceleration in towards the center here. In order to calculate the tangential acceleration, we already have an equation for that. That is, A tangential is equal to the radius arm times the angular acceleration. We didn't call it tangential acceleration before, we just called it acceleration. But in fact, it is only one component of the complete acceleration. Just as we saw when we were dealing with projectiles, in that case we had a velocity going in the x direction and going in the y direction. This is kind of the same idea in the sense that we have two accelerations, in this case accelerations, not velocities, but we have two accelerations that are 90 degrees to each other. And so they form a triangle. So if we were to look at point 1 again, we can see that if I redraw it here, I'm going to say here is my tangential acceleration going straight down. This is at point 1. Okay? And if we add the component to it, which is our normal, the other component, normal acceleration, then the total acceleration would be the addition of those two. So this would be I'm going to go capital T for total acceleration. And so once we have those two components, we can say that the total acceleration, it's just using the Pythagorean theorem, is the normal acceleration squared plus the tangential acceleration squared, and then we take the square root of it. The question then becomes, how do we find the normal acceleration? We don't have an equation for that yet. And that's what we see in our next slide here. So our normal acceleration may be represented as follows. We have the normal acceleration is equal to v squared over r, so in terms of a linear velocity. And we also have it in terms of an angular velocity, omega squared r. So depending on what's given. In both cases, it is dependent on that radius arm, but we have equation 7 for a linear velocity and equation 8 for an angular velocity. Again, just a reminder that that normal acceleration acts inwardly along the radius. The total acceleration is the sum of the normal acceleration and the tangential acceleration, as we see over here. So that covers everything we need to know for this chapter. However, there are some important notes that I would like you to be thinking about when you're trying to complete the practice problems. First is that a particle's velocity is always tangent to the path. So there is not a normal and a tangential velocity. There's just the tangential velocity when we're dealing with angular motion. Okay, we can convert from an angular velocity to a tangential velocity. If initial velocity or displacement is positive, then acceleration is positive and deceleration is negative. So that hasn't changed from the previous chapter. That still holds true. One thing we haven't discussed here is the fact that mating pulleys and gears have the same tangential velocity. So again, I'm just going to draw a figure to help explain this. So if we have, I'm going to draw a circular body, and this just represents a gear. And then I'm going to draw a larger circular body. Okay, and so both of these are gears, both rotating about their centers, but they obviously have a contact point. There is a point of contact there. So we are going to assume that we'll call this gear B and this is gear A. So gear B is rotating counterclockwise with an angular velocity, and due to that contact, obviously our body B will be rotating then clockwise with an angular velocity. At that point of contact, what we're saying is we know that that velocity always has to be equivalent at that point of contact. So that will allow us to help solve some of these problems. So we do know that obviously this body has a larger radius, we'll assume something like 3 meters, and this one has a smaller radius, something like 1 meter. And remember that velocity is equal to the radius times the angular velocity. Okay, so let's assume for this particular problem that the angular velocity of body A is 1 rad per second. Using this equation then, we can determine what the velocity at that point of contact is, since we do know values for body A. We have radius A and we have the angular velocity at A. we know that those are both 1, so that would be 1 meter times 1 rad per second. And that would be then equal to 1 meter per second. We know then that the velocity, and we can say that that's the velocity at A, but that also equals the velocity of B at that point of contact. If that's true, then based on this, we can then determine the angular velocity of B. Even if that wasn't originally given, that's okay, because we know that VA has to equal VB. That means then that we can rewrite this. VB is equal to RB times omega B, and we would just rearrange to solve for omega B. So that would be 1 meters per second over the radius, which is 3 meters, and therefore omega B is equal to 0.33 rads per second. So what does this tell us? It tells us that because there is a point of contact between these two gears, they will have the same velocity at that point, but that does not mean that they have to have the same angular velocity. Why? Because they have differences in radius, right? So they are rotating at a different speed. And this is really important. This forms the basis of doing gears, designing gears to be able to change velocities from motors. We do that based on this fact that there is a ratio of radius to angular velocity. So tangential acceleration is the result of the time rate of change in the magnitude of velocity. So remember I was saying the tangential acceleration is due to a change in magnitude of velocity. So that's your tangential acceleration, whereas our normal acceleration is due to a change in direction of our velocity. So this component acts in the positive direction if the speed is increasing and opposite direction if the speed is decreasing. If tangential acceleration is constant, then equations 1, 2, and 3 apply. Those are our original 3 equations of motion for angular motion. Normal acceleration is the result of the time rate of change in the direction, so a change in direction of the particle's velocity. And this component always is directed towards the center of the curvature of path. So easy for gears or wheels, that goes towards just a straight line towards the center. The magnitude of normal acceleration is determined by applying equation 7. So those are just our equations that we see up here, equation 7, equation 8. Okay, for a rotating object, a normal acceleration is 0, but a tangential acceleration may be present if the angular velocity is 0. Whereas in tangential acceleration may be 0, but a normal acceleration may be present if the angular acceleration is 0. I just want you to think about that for a little bit. Make sure that makes sense to you. That has to do with basically with this point right here, as well as the other point up here as well too, okay? This is what basically a summary of what we just said there. So the total acceleration is the vector sum of the tangential and normal acceleration. Remember, that's AT is equal to that squared plus that squared, just using the Pythagorean theorem. Okay, so here is the suggested homework and readings. I've already given you some of these practice problems to complete. And we're going to go ahead now and do a few practice problems to solve normal and tangential accelerations. We'll start with problem 1159 from the textbook, and this can be found on page 385. This problem, it states a 3-foot-long member pinned at one end accelerates from 2 RPM to 10 RPM in 6 seconds. Determine the total acceleration of the outer end when t equals 6 seconds. So it sounds like a fairly simple problem. However, one of the key words here is total, for total acceleration. That should indicate that we are having to calculate both a tangential and a normal acceleration. So let's start by just drawing a very simple figure of what's happening here. So we want to determine the total acceleration of the outer end when t equals 6 seconds. And I said the key word here is total acceleration. Given the fact that it is changing, that point is changing both direction and magnitude, we know then that there should be both a tangential and normal acceleration. So we can draw those in our figure here, where we have, remember, tangential acceleration, I'm going to call that AT, is 90 degrees to that radius arm. And our normal acceleration goes back towards the center. The first thing I always ask you to do is make sure that all of the known values are in their base units. And we see that that is not the case because we have velocities given in RPMs. Omega naught is equal to 2 rotations, or you can call that revolutions per minute. So we're going to get rid of minutes. There is 1 minute per 60 seconds. We're going to get rid of rotations, and there's 1 rotation or revolution per 2 pi rads. So our minutes and minutes will go away, rotations will go away, and we'll be left with rads per second, which are base units. So rads per second. Similarly, omega 1 is equal to 2 rotations per minute, and times 1 minute per 60 seconds, times 2 pi rads per rotation. Rads, rotation cancel out, minute cancel out, and we're left with 1.05 rads per second. Okay, so in order to determine first our tangential acceleration, we will need to know what the angular acceleration is. And that can be found by using one of our first equations given to us for finding angular acceleration. That would be our delta omega, so a change in velocity over the change in time. So that would be our omega 1 minus omega naught over t1 minus t naught, which is just equal to 1.05 rads per second minus 0.21 rads per second over 6 seconds minus 0 seconds. So we get 0.14 rads per second squared. Now that we have our angular acceleration, we can use our conversion equation. So our tangential acceleration is equal to r times alpha, which is equal to 3 feet, which is given. That's the length of that arm that's rotating, times 0.14 rads per second squared. So that gives us 0.42 feet per second squared. So we've just converted that, but that does give us a tangential acceleration. Next, we'll need to find the normal acceleration. And we have 2 options here. We can either use, remember, one that has the linear velocity or the angular velocity. But we have an angular velocity here, final angular velocity. So why don't we use that? So that's omega 1 squared times r. So that would be 1.05 rads per second. We're going to square that times 3 feet. And that gives us 3.31 feet per second squared. Okay, so remember that the total acceleration then is equal to the square root of an squared plus a t squared. Okay, so that would be the square root of 3.31 feet per second squared. We're squaring that, plus 0.42 foot per second squared. Square that. So our total acceleration is 3.36 feet per second squared. Next, let's look at 1162. This is a really good question because it forces you to really think about how you find your tangent. So what is the radius arm in this case? It's very important. So we have an object and it rotates about 0.8. So similar to the last problem, it accelerates from an initial speed to a final speed in a given amount of time. And we want to determine the total acceleration of a particular point on this object. So that's what we're going to do. I'm going to start by drawing out the figure, put all the unknowns in, and then we'll start figuring out how we're going to solve this. It's pretty similar to the last one, except the object looks different. And we want to determine the total. So again, a good indication there that we need to find normal and tangential acceleration because we want to find the total acceleration of point B. Now in the figure that's given, it shows point B at the top left corner. I'm going to do it here at the top bottom right corner. It really doesn't matter, and that's why I'm going to do this just to show you, only because it's symmetric. First, what we want to do, now that we've drawn our figure, we want to take all of our knowns, make sure we're in base units. Similar to the last problem, we see we have an initial velocity, final velocity that need to be converted to base units, so let's go ahead and do that. So our minutes and minutes cancel out, our rotation cancel out, and we're left with an initial velocity of 1.05 rads per second. 40 rotations per minute. Same deal. So you can see I'm just using the same conversion each time. And our units, you can see, work out. Okay, so from there, we know we can calculate an angular velocity by using the equation delta omega over delta t. So that's 4.19 rads per second minus 1.05 rads per second over an initial and final time, or final time minus our initial time, which is 5 minus 0 seconds, gives us 0.63 rads per second squared. Okay, so we need to determine the tangential. If we did like last problem, we're going to find the tangential acceleration first. So that would be A is equal to R alpha. But here's the problem, is that we do have an angular acceleration, but we need the radius arm. So the radius arm, it's not 4 meters and it's not 3 meters. It is the displacement between A and B. It is the shortest distance between whatever point you're trying to find on the body to the point of rotation. And so if we were to draw that out here, that would just be a straight line from A to B. If I did it up to the left-hand corner, it would be the same effect. Why? Because what we've done is we've essentially completed a triangle here that is 3 meters by 4 meters. And so our radius arm would then be 5 meters. And it is the same whether we locate B at the bottom right or at the top left. So our R is 5 meters. From here now we can actually draw, just to help visualize, where the tangential, normal, and total acceleration is being applied. That would be located, remember, always tangent to that radius arm. So there's our AT. We have our AN inwards. Okay, and so if you were to draw a little box here, then the sum of it would be, that would be our total right here. Total acceleration. So let's go ahead and sub in our values here we're going to have 5 meters for our radius arm times our angular acceleration that we just found. So 0.63 rads per second squared gives us tangential acceleration of 3.14 meters per second squared. Next, we have a normal acceleration, and that's equal to omega squared times r. So that would be equal to 4.19 rads per second. So we're going to use our final velocity here. We're going to square that times 5 meters. Gives us 87.8 meters per second squared. So our total acceleration then is going to be 3.14 meters per second squared. We're going to square it, plus 87.8 meters per second squared. Square that term. And our total, since we have a very large number, 87.8, and a very small number, when you're using the Pythagorean theorem, you'll find that it is going to be, that value always has to be a bit, it'll always be bigger, but since we have one way bigger than the other, it'll be very close to that larger number. So we actually end up with 87.9 meters per second squared. So clearly the normal acceleration here drives the total acceleration.